Today will be a short memo. We're going to talk about probability, what it is, what's the intuition, what's the concept behind it, and why do this. Probability is our way to formalize mathematically or quantify the concept of plausibility, which is about how believable, so it's what belief or how believable an event is. And when I say, oh, there's going to be a huge earthquake in Metro Manila tomorrow, how plausible is that? How believable is that? Do you believe me? And how do you quantify that belief? That's what probability aims to quantify. Now, there are two main categories or types of probability: the frequentist perspective and the Bayesian perspective. The frequentist perspective is conceptualizing probability as proportion of an event. Meanwhile, the Bayesian concept is more direct. It more directly aims to quantify belief or plausibility. So we're going to focus more on the Bayesian concept of probability. And in order to understand probability, we need to first define and understand some concepts. An experiment or a random experiment is a process that leads to a random outcome. For example, coin flip 2 times. This is the experiment. You flip your coin 2 times, and you can have several possible outcomes. It could be heads, 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 tails, tails, heads, tails, tails. This set of all possible outcomes is called the sample space, denoted by omega. So this is our sample space, the set of possible outcomes from the random experiment. Now, we care about the probability or plausibility of an event with a certain property. For example, the probability of one head from 2 coin flips. You can see that from your heads, 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 tails, tails, heads, tails, tails, which is the set of all possible outcomes, you want to get to the number of heads to a number. So that's 2 heads, 1 head, and 0 heads. This space is again the sample space, omega. This space is called the target space, t. And you can see there has to be some sort of mapping from the sample space, omega, to the target space, t. And what is that mapping? This mapping from omega to t is what we call random variable. The random variable is a deterministic function. We denote it by x. That is our random variable. So x maps from the sample space to the target space. In other words, it maps, let's say, x of hh to a number that would be 2. Okay. So now going back to our question, what's the probability of one head from 2 coin flips? Where 1 is what we care about. So this set that contains 1 is what we care about. Let's call this set S, where S is a subset of your target space. Therefore, if there's a mapping from your set of all possible outcomes to your target space, so from your sample space to your target space, there must be a mapping from W, which is a subset of your sample space, to S, which is a subset of your target space, and S is what we care about. So now, we can define the probability distribution. The probability distribution, P, given your random variable X, maps from your S, which is a subset of your target space, to the probability of encountering the values in that S. In our case, the probability of encountering 1, which relates or maps to 1 head, and it maps to W, which is a subset of your sample space, where W is H, T, and TH. Now we can see the relationships between your W relates to S by your random variable, and S maps to the probability of encountering that set of values in S, given the random variable X. Again, recall what X does, which is it maps from W to S. So if we can visualize that this is your set of all outcomes from your random experiment, omega, this is what we're concerned with, W, which is heads, tails, and tails, heads in this example. This is your set of all possible values. That would be your target space. So your target space will have either 0 heads, 1 head, or 2 heads. And this is the point that we care about. So this is your S. It's equal to S because we care about the probability of getting 1 head. So we can see that W in your sample space maps directly to S in your target space. Again, this sample space contains outcomes from an experiment. This one contains attributes of those outcomes. So HT, an outcome inside W, maps to 1 inside S. Given that intuition, if we ask what's the probability of getting 1 head from 2 coin flips, it is asking, given the random variable which maps from W to S, what's the probability of getting S, your desired number in your target space? So example is 1. And that is equivalent to the probability of getting W, which are your outcomes, given X of W is part of S. So what does that mean? In our example, the probability of getting 1 equals the probability of getting HT and TH, because these are the outcomes that satisfy the random variable function X of W is an element of S. Because these are the only outcomes where X of HT is equal to 1 and X of TH is equal to 1. X of HH is equal to 2 and X of TT is equal to 0. So they're not included. So going back to our example, probability of 1 head from 2 fair coin flips, given that we know the mapping probability distribution P of X, S, we can denote this as P of X is equal to some X, where X is an element of S. In our case, S is equal to the set that contains 1 because that's what we care about. Therefore, this is P of X is equal to 1. And this is equivalent to the probability of your W, where W is HT and TH. To calculate this, we count the number of all possible outcomes in your sample space. And if your sample space now is HT, TH, HH, and TT, then it has 4 possible outcomes. And because P of S is equal to P of W, given X of W is an element of S, then it's like saying, what's the probability of HT and TH. And so we care about this, which is your W, and the number of elements in your W is equal to 2. Therefore, we calculate the probability of x equal to 1 is equal to W over how many outcomes there are in total. So that's 2 out of 4. That's 1/2. P of x equals 1 is equal to P of HT plus P of TH. And that's equal to 1/4 plus 1/4. Why? Because P of HT now becomes how many elements there are in that set. That's 1 divided by the total number of possible outcomes. This is equal to 1/4. Same with P of TH. So that's it.